Hello everyone, Kotongwane the Native God here. Right, today we'll be looking at a sub-unit on the topic forces called frameworks. Right, frameworks. Right, also sometimes referred to as roof trusses. Right, excuse me. Right, so from this lesson, you will get an idea as to how we approach problems based on frameworks or roof trusses. Right, now for problems based on roof trusses, right, in fact any problem based on forces, in fact, right, you have to look at if the system of forces, right, are in equilibrium or not. Right, now for frameworks or roof trusses in particular, you have a framework, right, these here, right, these are referred to as the members of the framework, right, or the roof truss. Right, the forces on the outside of the framework, we can simply refer to those as external forces. Right, now it is very important that for any and all problems based on frameworks or roof trusses, that the external forces, right, that the external forces are in equilibrium, meaning the sum of forces heading downwards must be equal to the sum of forces heading upward. Right, if that's the case, that is when you can actually attempt problems based on roof trusses. Right, the external forces or the vector sum of the forces of the external forces must be equal to 0, meaning that forces going down must be equal to forces going upward. Right, that way we are then able to apply the conditions of equilibrium, right, using the external forces, knowing very well that the system of external forces are in equilibrium. What that suggests is that our roof truss or our framework is in equilibrium as well. Right, now with our framework, once we've established that our framework is in equilibrium, virtue of the vector sum of forces of the external forces, once that has been established that yes, our external forces are in equilibrium, which means our framework is in equilibrium, what that tells us is that now on the framework, right, the members are joined using joints. So you have a joint here, right? The members here are joined with a joint. You have a joint here, you have a joint here, you have a joint there. Right? So the vector sum of the external forces being equal to 0 or being in equilibrium tells us that each of the forces that these joints are joining, or each of the forces that these joints are being subjected to, are actually keeping these joints in equilibrium. Right, so meaningly, it takes, in terms of the framework or in terms of the members, it takes this member and this member, right, to keep this joint in equilibrium. It takes this member, this member, this member, this member to keep this joint in equilibrium. Right, it takes this member, this member, this member to keep this joint in equilibrium. Similarly with this one and also that one. Right, that is what the external forces being in equilibrium suggests. That is what it tells us. That is what we must take away from it. Right, now here we have 4 external forces, right? The 40, the 20, and the 2 reactions, the left reaction and the right reaction. Right, so before having to determine what they want us to determine, right? Sometimes it is, how can I put this? Sometimes it is necessary that we first calculate the two reactions, right? But before we just jump on to calculating the reactions L and R, let's first see if it is necessary for us to calculate both or just one of them, right? And the problem statement reads as follows: calculate the magnitude and nature of members AB, right? So member AB is this one, AB, so that's this member. And BC, you have B, you have C, so they're referring to this member, right? So member BC is this member, member AB is this member for the frame below, right? So they want us to calculate the magnitude and nature of these two members, AB, which is this one, and BC, which is this one, right? Now, at this level, there are, let me first say, there are a number of approaches that we can take in solving problems based on frameworks, right? We can take the graphical approach, right? We also can take the analytical approach. Analytical approach, we are able to use the conditions of equilibrium analytically, right, to determine whatever it is we need to determine here. But in doing so, there are also, say, two methods that you are able to use, right? One is known as the method of sections, right? One is known as the method of sections, right? And the other one is known as joints method, right? Now, this one perhaps you will get to use in strength of materials when you guys look at frameworks in strength of materials N5, right? I do not make use of this one, right? It's unnecessary for this level, right? I make use of the joints method, where we look at the forces that the joints is being subjected to, right, based on which members you need to determine, right? For instance, here you have to determine this member, and both members, right, are joined by this joint. So we will use the method of joints, right, seeing that the members we are looking for, right, are keeping this particular joint in equilibrium, right? So for N3 in particular, we are able to use the method of joints, or the joints method, and that's the one we are going to make use of. Now, making use of the joints method, right, will need for us to use it in conjunction with the triangle law, right? I did explain what the triangle law is, I believe, in the first video, right, on the playlist for module 3 forces, right? If you haven't watched this video and you landed on this one, I would suggest that you go and watch that video first, right? The link is in the description, right? So we make use of the method of joints in conjunction with the triangle law, right? Now, the triangle law essentially states that if you have three coplanar concurrent forces keeping a body in equilibrium, right, you are able to use those three forces, right, to construct a triangle, the direction of which must follow a head-to-tail direction, right? The head-to-tail direction essentially tells us that the triangle is closed. If the triangle is closed, it means the forces that you are using, or the vectors that you are using, are in equilibrium, right? So essentially, right, because you are using, or we are using, the method of joints, right, looking at just this one joint, right, we then look at the forces that this joint is being subjected to, right? And it will be this force based on this member, this force based on this member, and this external force, which essentially tells us that the three forces are keeping this joint in equilibrium, right? Which is why we are able to use the triangle law, right? Now, in terms of the nature of the force, right? So we use the triangle law, right, to determine the magnitude as well as nature of the members, right? Now, in determining the nature of the members, when we talk of the nature of the members, right, the nature of members, right, essentially you have member AB, member BC, and then you have this external force, right? So in terms of the nature of the members, a member is either a strut, right? A member is either a strut. Now, a member, or the nature of the member that we call a strut, is a force, essentially, let's say a force that resists, let me put it like that, a force that resists compressive forces, right? So a member, or the nature thereof of a member, is a strut if the member is such that it resists compressive forces, right? So members that resist compressive forces are forces that tend to go in this direction, right? So for instance, maybe let me do this like this rather. So they say this is your member. You have a joint here. You have a joint at this point, right? So a member would be considered to be a strut if the direction of that member is this one, right? So what this member essentially does is that it resists, right, compressive forces. A compressive force is one that seeks to crush a member, right? So a compressive force would be one that is going in this direction. So a strut member is one that resists compressive forces, right? So if essentially the nature of a member is such that the direction of it is heading towards a joint, right? Heading towards a joint, that suggests that that member is a strut. And then a tie, right? So essentially you get two types of natures of a member, strut and a tie. Right? Now a tie is a force that resists tensile forces, right? It is a force or a member that resists tensile forces, right? So the kind of forces that are tenacious, right? Let's draw this again. So it resists tenacious forces, right? So tenacious forces would be forces They tend to do that, right? Trying to expand a member, right, in this direction, right? These are the direction, or this is the direction of a tenacious force, right? So to resist that, a tie member, or a member that is tie in nature, tends to go in this direction, right? It resists tenacious or tensile forces, right? Now, if you look at the direction of the member in terms of, or from the perspective of the joints, the direction of a tie goes away from the joints. So if the direction of the member is heading towards a joint, you take it as a strut. And if the direction of a member is heading away from the joint, you take it as a tie, right? So towards the joint is a strut, away from the joint is a tie, right? I hope that part is clear. So that is what they mean when they say calculate the magnitude and the nature, right? So the nature, essentially, we can say direction, right, if you will, because essentially we determine the nature of a member by looking at the direction of the force or direction of the member, right? Right. Now they're looking for member A, B, and BC, right? Essentially, at this point, we have three unknowns. At this point, we do not know L. It hasn't been given to us. We don't know AB. We don't know BC, right? But the one thing you can tell here is that we don't necessarily need to calculate R, right? Because we are using this joint, right? So we don't necessarily need R, but we do need L. And because L hasn't been given to us, we are going to apply conditions of equilibrium to get the magnitude of L. The direction has already been given to us. It's up, right? So using the law of moments, we are going to determine the external force, R, right? Now, just a quick one here. See, they haven't mentioned that this framework is in equilibrium, which is wrong, right? They should have told us that this is in equilibrium, right? But maybe another way you can look at it is that the fact that we even have a framework means that the framework is in equilibrium, because if it wasn't, I'd imagine this would have fallen apart. Right? This is looking at it from a practical perspective, that this would have fallen apart and would essentially have absolutely nothing, right? Because if it's not balanced, right, then it could easily crumble. Hence, we'd have absolutely nothing here. So the fact that we do have a frame, we assume that the frame is in equilibrium, right? Another way you can check is if you've been given the magnitude of all the external forces, right? If you've been given all the magnitude of all the forces, then of course, to check if they are in equilibrium, then you simply use, right, this condition of equilibrium, right, to test if really the forces going up are equal to the forces going down. That's another way you can express this: sum of forces going up equal to sum of forces going down. Right? Right. So let's first calculate the external force external force L, using conditions of equilibrium, or using the law of moments. The law of moments is a condition of equilibrium. So because we are looking for L, we are going to take moments about R. Right? So we say here, take moments about R. Right? So taking moments about R, sum of clockwise moments is equal to the sum of anti-clockwise moments. Right? That's the law of moments. sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point. Right, that is how you state the law of moments. Right, so in calculating a force that is on the external forces, right, you only make use of external forces. So here, we have this, right? So now we look at the turning effects that each of these forces has towards the point we are taking moments about, right? This one is heading upward. If it's heading upward, it means the turning effect will be clockwise, right? The turning effect towards the point we are taking moments about, right? This is where we are taking moments about. The turning effect towards that point is clockwise. So we know that has a clockwise turning effect. The 40 kilonewtons is heading downward. The turning effect it has towards point R is anti-clockwise. So this one is anti-clockwise. Right. Similarly with this one, the 20 kilonewtons also has a anti-clockwise turning effect towards R. So this one is anti-clockwise as well. Right. Once that has been determined, you now can calculate using the law of moments, right? The magnitude of L, right? Now here you've been given this distance and this distance, right? That's 3, and from here to here is also 3, meaning from L to R is 6, right? Now what about from where this force is acting, which is at this point, to R? What is the distance between here and R? We know that's 3, but what is this distance? Now you look at the kind of triangle, right, that your members are making. If you look at this triangle, right, 60 degrees here, 60 degrees there, meaning that's 60 degrees, which means this is an equilateral triangle, meaning sides are equal, angles also equal. So if this side of this triangle is 3, it means this is also 3, and that's also 3. Similarly, with all the triangles, right, you have 60, 60, that's 60, meaning that's also an equilateral triangle. We know the one side is 3, it means this side is 3, and that side is 3 meters as well. Right? Right. So, meaningly, because we are looking for this side, right? We're looking for one of these sides, right? We know this angle is 3, right? Now, once you draw a line, right, that splits the two triangles into 2, the two triangles will be right angled, right? Meaning that if we are going to be using this triangle, right, using the angle 60, right, this side becomes the hypotenuse of this triangle, right? So if you're looking for that distance, right, the distance that we're looking for, which is this one, is adjacent to the angle, right? So because it's adjacent to the angle, it means that side is essentially 3 cos 60, right? Even if you use this side, it'll also be 3 cos 60. Now 3 cos 60 is equal to 1,5. Yes. So essentially what this means is that from here to here is 1,5. So this is also 1,5. Right. Similarly with this one. Right. It means that's 1,5 and that's 1,5. Right. Right, so we've worked out our distances. Now you can apply the law of moments mathematically to get the value of L. Now L is clockwise, so L will be on this side. So L times the distance from L to where we are taking moments about. So from here to there, which is 3 plus 3, that's 6. So So 6, that's the only force that has a clockwise turning effect. The other two have an anti-clockwise turning effect. So the 40, so you have the 40 times the distance between 40 and where we are taking moments about, that's 1,5, that's 3, so that's 4,5. So times 4,5 plus the 20, and the 20 times the distance from 20 to where we are taking moments about, 1,5. Right, so that's 20 times 1,5. Right. Now, however you choose to proceed here mathematically will be up to you. I'm simply going to divide this by 6. Right. We are looking for L. And then if you punch this in your calculators, you are going to get 35 kilonewtons. Right. So L is 35 kilonewtons. Right. So now we have L. So we'll be able to get member AB and member BC, right, using the method of joints in conjunction with the triangle law. Right. Right. Now, remember with the triangle law, if you have 3 forces, right, 3 coplanar and concurrent forces, right, keeping a body in equilibrium, then those 3 forces can be used to construct the sides of a closed triangle, right, the direction of which must follow a head to tail direction. Now we have 3 forces, right, this member, and this external force, right, keeping this joint in equilibrium. So we are able to apply the triangle law. Now, how are we going to apply the triangle law here? We know one force is heading upward. Let's say using the triangle law. Right. We know one of the forces is heading upward. Right. We know this force is heading upward. Right. That force is force L. Right. Now, in constructing the triangle or the sides of a triangle, you must make sure that, right, you stick to the directions that have been given. Now, we do not have the direction of this one, nor the one for this one, but we have the direction of L. It's heading upward. So you draw L heading in the direction that has been given, which is upward. Right, so this is L. L is 35 kilonewtons in magnitude. Right. Right. Now the other 2 members, right, you have member AB and member BC. Now the 2 members, right, are forming an angle of 60 degrees with one another. Right. So all we do here in completing this triangle, right, we must make certain that member AB and BC are forming an angle of 60 degrees. Right, an angle of 60 degrees. Now we've already drawn the external force. Now we draw this member, right, and then the last member, which is BC. So we know that's A, that's B, and that's C. So that's member AB, member BC, forming here an angle of 60 degrees. Right, so we know this member is heading upward, hence it's heading upward. Right, and then the other 2 members, we know they are making an angle of 60 degrees from one another. Right, which is exactly what we have here. Right, now in terms of direction, remember we are using the triangle law. And the triangle law, right, states that, or in part of what it states, right, it does mention that the direction of the vectors that complete the sides of a triangle must follow a head to tail direction, which means if this one is heading upward, right, as per the framework, it means this one is definitely headed in that direction. This one is headed in this direction, right, thus following a head to tail direction, right? And then if this one is headed in this direction, it means this one is headed in that direction. So this one is headed in that direction, right? Hence following a head to tail direction. Head to tail direction means that the directions are essentially following each other, right? You don't find one that is coming to meet the previous one, right? Each of the directions are following a head to tail direction, right? That is how you use the triangle law in conjunction with method of joints for frameworks, right? Now here we obviously have a right angled triangle, so we are able to use our trig ratios, right? You have saw, you have car, you have tor, right? Because the triangle constructed is a right angled triangle, right? Right, it means we can use these mathematically to get what we are looking for, right? So first, now remember, maybe I'll get to that later. Right, so let's first calculate these members. Right, so we'll first calculate member AB and then BC. Now, member AB is essentially the hypotenuse of this triangle, right? The angle we have is this one, and the side we have is this one. So you look at the relationships of the sides we are going to use in conjunction with the angle that we have, right? So the side that we have is opposite the angle, right? And then this side is the hypotenuse. So you then decide based on what we have, the side that's opposite the angle and the hypotenuse, because that is what we have. It means we are going to use sine, because it's only with sine theta that we look at the side opposite the angle, which is this one, divided by the hypotenuse, which is the side we're looking for. So here we have sine, the angle is 60, is equal to the side opposite, which is the 35 kilonewtons, divided by the hypotenuse, which is AB. Right, then you solve for AB here, making AB the subject of the formula. This will be equal to 35 divided by sine 60. Right? Then if you punch that in your calculators, you should get 40,415 kilonewtons. Right? That's the magnitude of member AB. Now we have to state the nature of the member. Right? How do you state the nature of the member? You look at the direction. Right? You look at the direction of member AB using the triangle that we constructed. Right? It is headed downward. Right? Remember here, this is your joint. So if this is member AB, right, as per the triangle law, this is headed in that direction. Right, this is headed in this direction, right, which is towards the joint. Right, so this side, it will be headed in that direction, which again is towards the joint. If it's headed towards the joints, that means it is a strut. So this here is a strut. So that the strut, we have both the magnitude and nature of the member AB. Now we move on to BC. Right, now side BC is adjacent to the angle, and the side we have is opposite the angle. So based on that, which of these, right, must we use? The side we have is adjacent to the angle. The side we are looking for, BC, is adjacent to the angle. The side we have is opposite the angle. So we use TOR, tan theta. So tan 60 is equal to the side opposite, which is 35, divided by the side adjacent, which is BC. Now you make BC the subject. BC is equal to 35 divided by tan 60. Right? Now 35 divided by tan 60 should give you 20,207 kilonewtons. So this here is the magnitude of BC. In terms of the nature, we go back to a triangle. You look at the direction of the triangle. We look at the direction of the member, BC. Right? It is headed in that direction, meaning here, right, this is headed in that direction. Right? If it's headed in this direction, right, it means it is going away from the joint that we are looking at. Right? It is headed away from the joint that we're looking at. Because it's headed away from the joint, it means it is a tie. So this here is a tie. Right? And that is how you determine the magnitude and direction of members on a framework or a roof truss for engineering science M3 under forces. Right? I trust this was helpful. If it was, please like the video, subscribe to the channel, and turn on the notification bell so you do not miss out on any further content. Right? All the best. Nated God signing out.